Hello everyone, I'm Zhichen Sun from Peking University. Today I would like to share our CPR work, regularizing second-order influences for continual learning. First, we begin with a quick preview. In this paper, we address the problem of continual learning on long task sequences, which faces the main challenge of catastrophic forgetting. To address this challenge, the prevalent method retains knowledge by rehearsing on a small replay buffer, which requires careful sample selection. However, existing selection strategies are primarily designed for single-run selection, which neglects the interactions between selection steps. Motivated by this, we propose to model the interactions with influence functions and address it with a novel selection strategy. Next, let's delve into details. While machine learning models have been widely adopted in many fields, they have yet to accumulate knowledge like we humans do throughout our lives. Continual learning has hence emerged to study the training of models on long task sequences with a potential data distribution shift. It is known for suffering from catastrophic forgetting, where the model abruptly forgets past knowledge after being updated on new tasks. To mitigate forgetting, the most effective method by far is based on memory replay, which buffers a small call set of training data for later rehearsal. Due to the memory constraint on the replay buffer, a careful sample selection strategy is needed during the process. However, existing selection strategies are primarily focused on refining single-run performance, which neglects the interactions between selection steps through the data flow. The main contribution of our work is that we model the interactions between consecutive selection steps in continual learning with the tool of influence functions and identify a new class of second-order influences. Then, a novel regularizer is proposed to mitigate second-order influences, which also has clear connections to two other popular selection criteria. We start with a formulation of replay-based continual learning. Consider learning on a stream of data with a small call set. The goal of call set selection is to preserve performance on all available data by replaying on that call set, which is formulated as a bi-level optimization problem. In the following, we will first present a greedy solution based on influence functions, then showcase its limitations and propose our improved version. To solve the bi-level optimization problem, we linearly approximate the effect of selecting each sample by perturbing its weight. Then, a classic result gives the influence of upweighting that sample on the auto loss. To minimize the auto loss, one should greedily select the samples with the lowest negative influences, which yields a solution that is optimal under linear approximations. While this greedy selection strategy is qualified in many evaluations, it overlooks the interaction between selection steps. Here is an intuitive illustration of its second-order effect. Since the strategy always favors similar samples to the existing ones, the call set will gradually become more biased and less diversified over time, leading to inaccurate influence estimates and degradation of future selection. To model such an effect, we are inspired by the derivation of influence functions and upweight two samples from consecutive selection steps. The upweighting of the previous sample would influence subsequent selection by interfering with the influence estimation. Specifically, there are two cases that depend on whether the two samples are jointly optimized in the next round or not, resulting in two cases of second-order influences. Since these second-order influences interferes with future selection, we naturally want to minimize their total interference, which can be represented as their weighted sum with a coefficient mu. While the total interference is intractable, it turns out that its upper bound can be effectively optimized. We then derive a new regularizer that can be combined with the first-order influence to serve as our final selection criteria. To understand this regularizer more intuitively, we interpret it by connecting to two widely used selection criteria. When the hyperparameter mu is 0, it is equivalent to the rule of gradient matching, and in the more general case where mu is greater than 0, we simplify the formulation by assuming an identical Hessian across all samples, from which one can see that our regularizer promotes sample diversity. Moreover, the proposed regularizer excels in incorporating additional Hessian-related information, which proves to be useful in experiments. The proposed method is evaluated on 3 continual learning benchmarks, including SplitCFR10, SplitCFR100, and SplitMiniMGNet. The results on SplitCFR10 show that our approach consistently achieves the highest performance as well as the lowest forgetting. In particular, in the more difficult class incremental setting with the smallest memory, the improvement reaches up to 5 to 6 points. Similar improvements are also observed on the more challenging benchmark SplitMiniMGNet. Furthermore, we perform application studies to justify the designs of our approach. As shown in the left figure, both hyperparameters corresponding to different designs contribute to the final performance. And in the right figure, the use of our proposed regularizer significantly improves the influence estimation accuracy. As a result, our place-based method can achieve better performance in continual learning. If you are interested in our work, please check out the code from the link below. That's all. Thanks for listening.